Hi, everybody. Okay, let's see what we got. Yeah, go ahead, Joshua.
All right, really quick. Did you notice that you probably got less responses on the red black or the last quiz for
Yeah,
last
they're in the
week?
wrong guide. Yes.
Yeah.
Yeah, I know. I mentioned it to the. It's funny because one of the TAs is like, "Oh, it's in the wrong guide," but then somehow it didn't get moved. Like the
Okay.
observation was made, but then it never got moved.
Because I didn't get to do it until this morning. I was looking for this week's or
Yes.
today's check-in exercise, and then I found Friday. I was like, oh man, I was looking everywhere for that.
Yeah. Yep. Sorry about that.
Okay.
What happened was we moved the KD tree lecture up, the one that I re-recorded, 3, and then moved everything else down, and then some like one slip happened in the infrastructure, which left everything slightly weird. Sorry. Yeah. And we moved it because we wanted to switch project 2A and 2B, the ordering, because it turns out that we had them backwards last time. Like the theme last time wasn't as good. So yeah, it makes more sense. Because what is now 2B is a little bit harder. And it makes sense to have a slightly harder one later. Cool. What else you guys got? Today's lecture, hashing. This is probably the most famous thing in the whole class. Like the thing you're most likely to get asked about at some kind of interview someday. I'll just throw that out there.
What types of things about hashing would we be asked about? I already knew like a bit about hashing
Yeah.
from like experience as a web developer,
Mm-hmm.
but like, so what, like the general concept is what we're going to be asked about, or
Yeah,
like
I
the
think so.
methods we
Just
use to actually do it, or
I think it's understanding the general concept. Like, what is a hash table? Like, what's it all about? Because there's a number of interesting things, like, the idea that in a given programming language, that they tend to support a hash function. So, like, knowing what a hash function is supposed to return and how it's used and what can go wrong if the hash function is implemented incorrectly. I think those are the key ideas. Yeah. And if someone goes extra hardcore, I guess they would ask about the fact that the hash table needs to resize in order to maintain its good performance. Um, and yeah, even I guess talking about how things can theoretically go wrong is also, I think, some people find interesting. Just like, suppose you have a web uh, forum where your users are stored as a hash table for looking up usernames or whatever, or like your password database. So I think I can imagine someone wanting to ask the question about like, well, what's the worst thing that could happen, and being able to say, oh well, if someone does an attack where they make a bunch of usernames that all hash the same thing, then you end up with potentially a linear time lookup function. I think that kind of thing could come up maybe. Yeah.
there
What
was
is
all
the
the
really?
drama way back when with like when MD5 was found to just have collisions everywhere, and then
Mm-hmm.
people started getting compromised left and right because it was
Yes.
exploitable.
Yes. Totally. Um, what's interesting is that the Java hash table, it actually stores the individual buckets not as lists but as red-black trees, if possible, if the items are comparable. There's some weird, as I recall, like it's something like this. There's some funny, because that way, even if everything hashes to the same bucket, you end up with good performance because you're just using a tree of some kind, assuming that the items have a comparable. Um, and I don't remember. There's some weird magic in the way they implemented it, where if the generic type you're given is comparable, then it uses trees. Otherwise, it doesn't. But I had to go look at the code again. I remember looking at it being like, "Oh, this is awesome and crazy." But it's a good question. I'd like to know. I mean, I've always wanted to go and just do software job internships so that I can, or like interviews, so that I can see what you guys get asked. Um, I did get an email, which I'll drop in the chat here, which I thought was nice, from a student from 2017. So, by the way, in 3 or 4 years, feel free to email me with what's going on. Um, let's see. All right, here you go. I'll draw. I'm putting in the compliment for myself. Sorry, I didn't filter it out, but whatever. All right, there you go. So the key point here, though, is that he thought 95% of the internship could be done after 61B and 90% of software engineering interview questions if you know the class well. So anyway, I don't know how true that is, but some random guy graduated a few years ago thinks so. All right, what else you guys want to know?
Could I ask a question about Lab 6? the
Sure.
like optional questions. Could we
Yeah.
go through those real quick?
Yep.
Awesome. Thank you.
What do you want to know about lab 6?
Like the optional questions at the end,
Oh,
like the
optional.
runtime
Okay,
analysis.
yeah. Let me look at them. Sure. Let's see. Okay, let me share my screen.
I think it's
Okay.
lab.
Yeah. Cool. Mm-hmm. Okay. Go ahead.
Oh wait, no, it's not lab 6. I think it might be lab 7. I'm sorry.
Oh, okay, got it.
Yeah, my bad.
Ah, okay. Sure. Okay. Optional. Okay.
Yeah.
Yeah. All right. Sure. Oh yeah, yeah, yeah. Okay.
All right.
These ones.
Yeah. Mm-hmm.
What do you want to know?
Oh, could we just like go through them all? Like,
Oh, sure. Okay, cool.
yeah. Sorry.
Let's see. True or false? All right. You're having a BST map, and it's not balanced necessarily. You have n items, and we want to know is put big O of log n. Okay. Well, do you mind if I ask you? I mean, I can just talk through them. But...
Yeah, that's false because it could be spindly.
Yeah, exactly. Great. So it could be spindly. Can't
Wait,
bound a
also,
bow. Yeah.
Also something's a ON. Could you call it theta n or no?
If something's ON, could you say it's theta n? Not necessarily.
But the other way is true.
Yes, correct.
Okay. All right.
Because think of theta, it's equal to. O is less than or equal to. So this thing's equal, and it is also less than or equal. That's the way I think about it.
Yeah.
All right. How about this one? As you said, spindly.
False again.
Yeah, great. All right. Is it theta n to put in
in
a tree?
I think that's false.
Correct. Yeah, and the reason is that it's only that in, I guess, a worst case scenario.
Right.
Yeah. So you could say it's theta n in the worst case. If you added the words in the worst case, it would be true, but it's not.
Right.
Okay. ON?
True.
Correct. That's
True.
one. Yeah, because it's an upper bound. All right, good. So you got all those fine.
Yeah.
All right, now we have this weirder thing.
Yeah, I didn't really understand that.
Yep. So this is from lecture.
I do remember it from lecture. I just don't remember like why that's the case.
Yeah. Let's see. Oh, this is an empirically derived fact. Let's see. Yes. So we didn't prove this in class, but it is something that one can prove. So I gave it as a trivia fact. If you
shouldn't it be log 2? Shouldn't it be log 2?
It's natural logarithm, actually. Yeah, I didn't prove it. Yeah. Will we? No, we won't. But yeah, I was trying to think of in quick sort if we talk about it at all, but we don't. This would be more of a CS 170 thing. I don't think they do this proof in CS 170, but you have to have you have to know what like the most natural proof for this. You have to have the notion of a random variable, which we have in our class. So yep, there's some calculus tricks. If you want, I could send you a reference for it, but yeah.
I think I'm good.
Okay.
I'll do like taking 170.
Got it. Okay, so if two keys are not equal, according to dot equals, C and K. Sort of a little funny because K is our generic type. I think this is probably a weird symbol to use, but okay.
I think that's true, right?
So running both of these, if they're not equal, running both of them takes at least log n time.
Wait, that's best case, right?
Well, it's not best case. It's just a lower bound on the amount of time.
Yeah, at least. Okay.
Yeah.
Because when would it be less? Oh, wait, no, that's not necessarily true. Wait, so no, that's false then.
Why do you think? Give me an example where it's not true. I agree with you, but.
Because if it like goes into the middle of the tree, it doesn't go all the way to the end and it's bushy. Or if it's like anywhere like before it reaches the end.
Sure. Yeah. I mean, the best way of putting it is like if C is always the root and K is always the left child of the root. Yeah. Right. Yep. This is a weird question. All right, fine. And then lastly, this one.
Like, okay, so this is the one I have most trouble with. Like, I
Mhm.
didn't know how to like visualize it, or like,
Okay, let me read it
there's
real
like
quick because I'm coming in cold because I haven't looked at this in a long time. So if we have a map which consists of a root key and two subtrees, that's right. B, okay. B, C, manager, C. Okay. Okay. I understand what number of nodes is. So then now let me read mystery real quick. So you're given a tree. And then we have Z. Okay, let's see. Interesting. I wonder how this was inspired, this question. I haven't looked at it in like 2 years now, so that's basically totally out of my brain. So the base case is Z is less than or equal. Okay, so it returns a key. All right. If Z is less than or equal to 0, or Z is greater than the number of nodes in the current tree, it gives nothing. Okay.
Mm-hmm.
Let's see. If the number of nodes in the left tree is Z minus 1, then we return the current item. Okay. If the number of items, we're just trying to find the runtime. We don't necessarily care about what it does. Okay. Sorry. I was trying to understand semantically what it does. Maybe that's unimportant. So if the number of nodes on the left is greater than Z, then we call this function on the left side. Otherwise, we look on the right side and we pass some weird Z. All right, this is a pretty epic problem.
Mm-hmm.
So I think what I would do, what I'm tempted to do, and I don't know if this is the right approach. I'm guessing this is some old, really hard exam problem. I'm tempted to create a tree and plug in some numbers and see what
Yeah, no,
happens.
that's what I did. And then I found like the worst case, like you would like pretty much go through all the nodes of a spindly tree.
Yeah.
And then like
Wait, what is it? What does it
I
do? Do you have a description of what Mystery's function is?
no,
Okay.
but it like goes down the left side unless like that else if
Mm-hmm.
thing. So I just like made it like go down all the way on the left side and pretty much got like you had to like traverse through like end nodes of a spindly tree.
Mm-hmm.
And then
Why is that the worst case, to go down the left side? Z gets called over and over.
yeah.
Okay.
And
What about
then
this? What does this do? So number of nodes, this function here. So let's say Z starts at like, some huge number.
The interesting thing is this looks like a tree of trees, not a tree of nodes, because we can pass b dot left to mystery, and b dot left has to be a BST map.
Yeah, I mean, it's a naked recursive tree. So we're passing raw nodes. BST map. These are yeah, the BST map you created is not naked recursive like this. B dot left. It's a weird question.
okay, so but if you
All right, so I'm gonna interrupt real quick just to address that. The BST map that you guys created, it doesn't have a dot left, right? Like the one you made in lab.
yeah,
No,
but yeah,
it just has a root, and the root
Yes.
is a node, and then the
Yes.
nodes have left and
Yes.
right.
yeah.
So
like
we would
this.
make this function with a node, not a BST
Correct.
map in the
Yeah.
argument.
So this was with the naked recursive tree in mind. I'm curious about the provenance of this question. Was this here last time? I bet it was. But what I don't remember. Funny. Okay. All right. Yes. I mean, that's I think of an important note. Not a super important one, but something to keep in mind. That this is assuming raw nodes, not actual BST maps. So anyway, all right. That's sort of a glitch in this lab, but
Wait,
whatever. We didn't pay attention.
what does that mean? Like raw, like naked
So that is this, if you replace this type with BST node or just node or whatever you called it in lab 7, then the problem makes sense.
With like the nested class.
Yeah, with the nested class node. Yep. Because right now, like B is the, kind of like with our A list, S list, D list, array deck, linked list deck, like the thing that you have a handle on is like, it's a middleman. It doesn't let you access the naked recursive data structure underneath or the array or whatever. So you shouldn't be able to say b.left. That doesn't make sense, but all right. That said, the intention of the problem was clear and your analysis is along the right lines. But yeah, just worth mentioning that this really should be BST node. Anyway, all right, so let's see.
Could I give you my thought process?
Yeah, give me your thought process. Yeah.
Okay, so if you go to the else statement, then like Z is gonna be like made to a smaller number, but if Z is like already a smaller number, then you're gonna keep hitting the else if statement over and over again. Like each time you're gonna go down like one notch in the so then let's say it's like a spindly tree that like has all left nodes and it's just gonna keep going down that line over and over and over again.
Yeah.
And it's gonna pretty much be like ON, and then it says like the runtime of the number of nodes has running time of theta n. So then it would be ON squared.
Let's see. Why would it be ON squared versus just ON if it just
because the number of nodes
number of nodes takes n. Yes, because you'd be doing n plus n minus 1 plus n minus 2 plus n minus 3. Yes, I think that's possible that that's the right analysis. The only place where I get a little nervous is, actually, so it goes down the tree here. Okay, yes. So in any case, it can never be worse than
going through each one.
Yeah, for these two cases, right? Like either way, if you keep calling these two cases over and over, the only thing that's going to happen is you're going down the tree one at a time. Yeah, so that would be
but if you go down the else statement, though, you're going to end earlier.
Let's see, this one here.
Yeah, because Z is getting smaller.
Yeah, but maybe like Z starts off as some absolute giant number. So maybe it's, well, I guess if Z is bigger than number of nodes, no. Okay, yeah, well, I guess what I'm just trying to bound is I don't even want to think about the Z right now. Just saying, like, if you did either this or this going down a tree, it's still going to be n squared. Yeah, I think that's a reasonable argument. And then here, these two cases would be constant. Okay, what I was trying to leave room for is the danger that there would maybe be another call where it calls mystery on the current node, but only Z changes. Because in that case, the runtime could actually include the value Z in it somewhere. But I think what you have in mind...
Can you say that one more time?
Yeah, let me take this code and make another version real quick. So I don't know that this actually works. I'm just trying to imagine if some other...
You can't see your...
I'm about to, sorry.
Okay.
Thank you. So let's say I added, what I just added was, sorry, actually, I'll show you the change. So it looked like that. Let's say it looked like, I don't know, blah, blah, blah. Like, I don't know what's here. Then we had return mystery B Z. Let's see. I don't know. Let's just do like Z minus 1, whatever. Like, if you did something like this, then maybe the runtime would be dominated by, like, the Z would affect your runtime. Like, you might end up with like a runtime that's like big O of n squared plus Z. I don't know. Like, I'm trying to imagine some weird situation like this. Like, I don't know what it would be, but basically, if you're making calls to the same node with some function of Z here, where I don't know what F is, then you can have a runtime that would involve Z and not N. Does it make sense? Yeah, I don't know what that would be, but I could just see the possibility in my like mean final exam writing mode. But that would be a really weird and hard question.
Yeah.
Okay. Now I think what go ahead.
No, just like the complexity.
I mean, the thing about these problems is they can become arbitrarily complex. So like you may remember that with disjoint sets that the runtime of weighted quick union with path compression is the inverse Ackermann function, which is a pretty complicated function. Like runtimes can get however weird you want if you write weird code. So I think that the takeaway for me, if I had to guess, thinking back to when this problem may have been written, the goal was not to understand what mystery did, or even to really understand what Z works or how it works. It's to make that observation exactly as you did, that really what matters is the fact that in the worst case, you're going to either be going down the left spine of a spindly tree and the right or the right spine of a spindly tree that goes down to the right. So I think it's fair to say that big O of n squared, because we're going down the left spine of a spindly tree. I think that is a perfect.
Or you would go right and then left.
Yeah, right. Then more or less, right? Yeah.
Yeah.
Wait,
Alright.
so why is this n squared and not n? It looks like you
because
can't go
number
over
of
any node
nodes,
more than once.
it calls number of nodes every time it goes down. So number of nodes is big O of n time. Does it make sense? So let's make up a tree like 9, 8, 7, 6, 5, 4, 3, 2, 1. All right. And this incidentally is the number of nodes, but it's also the value in there. And let's say we pass in z equal to 8 or something. So in that case, we'd get to this first part and we'd call if number of nodes. So that would take time 9 to finish. Sorry, let's say. So the way I'm thinking about this is, here, let me copy and paste this down here. So we're plugging in 8 here. All right. So we're calling this with 8. Actually, how about this? Mystery on, I'm just making a notation. So when we call mystery node 9 with 8, this calls number of nodes node 9, which takes time 9. Do you agree with that fact?
Oh, I think I get it now. I just I didn't see that number of nodes took theta n, because the way I implemented BST tree, I mostly went off like the Princeton one as like a thing, and they track number of nodes as like a constant in each node.
Got it. Yep, correct. Yep. So if you cache the size of the tree so that number of nodes takes constant time, then you'd be in good shape. Anyway, all right, that's a cool question. This is a really mean question, but it's all about drowning you in complexity and making you identify what actually matters. But this is a pretty damn hard problem. All right, cool. Actually, for anybody who didn't quite follow that, I guess I'll just do a tiny bit more, which is this makes a recursive call to mystery node. So if the number of nodes, let's just to finish this off, the number of nodes b dot left is greater than 8. Maybe I should have picked a different z, huh?
Yeah, just pick like a low number, yeah.
Yeah, 1. All right, there you go. Make sure cursor call the mystery node 8, comma 1. All right, then mystery. There we go. Thank you. I think your analysis was great. That's what I would say.
Thank you.
So this calls number of nodes node 8 takes. Sorry, it's just 9. And this is kind of a loose proof, but I think it makes the point. And so forth. All right. Okay. What else do we have? Sufi.
Yeah. Can I share my screen?
Yeah.
Thank you, Professor.
You got it. Thank you. That's a fun question. I'm glad someone subjected it to us in the past. All right. Sorry, Sufi. Here you go.
Okay.
All right. Should have the power now.
Okay, do you see my screen?
I do.
Okay, great. So I had a question about reverse here. So I think the answer is that it's theta n runtime.
Yeah.
But I wanted to so how I would maybe write this function is I would get a pointer all the way to the end, right? So that would take n time, and then you would have to go through it again, right? And that would take n time as well. So is it then 2n and that's why it's theta n? Because I first thought it might be n squared time.
Well, here's the funny thing. Reverse. You guys have never. There was no point where you wrote a reverse function anywhere, right, in this class for an int list?
I don't think so.
Yeah. I mean, we don't have an algorithm for it. I think you have a good argument for why it would be big O of n, because you need to at least get to the end of the list somehow. But yeah, actually, it turns out writing reverse, by the way, it's a really clever problem, really interesting, like shockingly fun. But it's a pretty hard math problem. You are right that if you had to go to the end of the list, so tell me about that second time. So you're saying you go to the end of the list to get the last item. Why do you need to go through it again?
Because you need to like switch the pointers, right? Or so you would have to like have maybe another pointer, because so you have to like set, okay, essentially you have to set your I'm trying to think, because like if you set your like current pointer, the one that was pointing to the front of the list, to the end of the list, then you kind of lose all of your other things because there's nothing pointing to it, right?
Yeah.
So
yeah.
Then I'm trying to think, like, how would you like keep track of that?
Yeah, no, it's actually pretty hard. I mean, it's a pretty deep question. There's an iterative solution, which is not too crazy to comprehend. And there's a recursive solution that is one of my favorite recursive algorithms in the whole world. So this worksheet, who created this worksheet out of curiosity? Is this staff created, or?
This is one of the topical review sessions that I think the tutors held.
Yes. So I would say that this problem is pretty hard to answer without having a reverse method in front of you, especially since we didn't actually provide one. Yeah, so I'm gonna say your intuition that it should be linear is correct. And let's say it was 2n, which is not quite right, it would still be theta n.
Okay.
Yeah.
It's like, I mean, at first I thought it was n squared though, and that's
well. So there is an n squared algorithm that's very easy to code up, which is go to the very end of the list, then go to the second to last thing in the list, and then like set the pointer, and then go to that like kind of scanning through the list, and then scanning through a little less, and then scanning through a little less, and a little less.
I think that's how I like maybe thought of like the implementation, and that's why I thought of n squared, but the answer was n, and so that's why I was confused, because
Got
I
it.
think
Well,
you have a different implementation.
The reason it was hard is because we haven't actually given you a reverse algorithm. You are absolutely right that naive algorithm that you thought of is indeed n squared, and it's easy to code up and it's easy to understand. The other algorithms are a little trickier, the ones that are n.
Okay.
Yeah, interesting. All right, I will make a note. Okay, let's see. All worksheet. Question about int list reverse question.
And then I had I think another question on this worksheet. So looking at these two right here.
Yeah.
So here it says that it runs in linear time with respect to the input.
Yeah.
So like clearly this is n, I mean, I think it's n cubed because it's running through this n times and then that n times, and then you have like a linear function call. So but then here it puts in a number into linear, and I'm pretty sure, like based on the answer, which is n log n, because I first got n squared log n squared, I'm pretty sure that should be constant based on the answer, but I'm kind of confused what they mean by like it runs in linear time with respect to input, and then here you put it in input and it doesn't run in linear time.
Yeah, so it's linear with respect to the input, which is set equal to 100. So that linear call is just a constant time operation. Does that make sense?
Kind of. Okay, well, so it's always set and it never changed. I mean,
yeah, it never changes. So like, let's just even simplify it a little and not make it recursive. Just say, like, imagine that the code is literally only the for loop. Does that make sense, what I'm asking?
Yeah.
So in that case, what would you think the runtime is? N squared or n?
Well, without the recursive calls. I would think it's... Well, I think the problem was that I thought that linear was n runtime, and so then I thought it would be n squared.
Got it. Okay. So
and that's actually
so as a thought experiment, imagine that instead of being linear 100, it was linear. Actually, how about this? let me give you an example of a piece of code that would be linear with respect to input. So imagine that the body of linear creates an array list and then adds the numbers 1 through n to the array list. Does that make sense?
Yeah.
Okay, so what's the runtime of that function with respect to the input? It would be theta what?
N.
Great. All right, now imagine that you call linear of 1. What does the function do with the array list?
I mean, it's constant.
Great, yeah, it creates an array list, adds 1 item, right? So here, think about linear 100. Like, yes, if you gave it, and this is this is a great question, I love it. If you gave it a specific number, like just say 100, that's not growing with n, right? As you increase the n, that's the argument to g, it's not changing the runtime of the linear function. Does that make sense?
Yeah. Okay.
Yeah.
So linear itself, like when you look at the actual like implementation of it, if you were to just look at linear, would you think it's n runtime?
Yeah, that one I described with the creating an array list and then adding the
So
first
that would
times.
be n runtime, but then because in this function right here, it's like constantly we're just putting 100 as an input, it's constant.
Correct. With respect to the n, that maybe the issue is actually one of symbols. So that g function that takes an argument n, that is a different n than the one that was fed to this hypothetical linear function that was created somewhere else.
Okay.
Does it make sense?
Yeah. I think it does.
Maybe a better way of putting it is, another way to make it concrete is imagine building one of those timing tables from Lab 5. And if you did it for this for loop, you would expect it to look linear, not squared, because the time it takes to actually create those linear 100 calls is constant. So the only thing that's growing is how many times you're calling linear 100, not the actual argument to linear.
Okay, got it. That makes sense.
Because at the end of the day, that's what we're really curious about is, if we build the timing table, how's it going to grow? Yeah. Great question. Love it. I'm so glad this was on the worksheet. That's pretty deep. It's fun. Yeah, it's a very
Sorry to interrupt, but to just carry on from there, just how we're adding linear 100 to every call of n, this is similar to how when we said in B trees, since we specified the L before even creating the B tree, although we are increasing time, but since you're increasing it by L for every n, it will be basically, it doesn't matter. It's a constant time with respect to L.
And L is the maximum number of things that can be in a node. Is that right?
Yeah.
That's absolutely right. Correct.
Okay.
Yeah. Because remember, the main goal of asymptotics is to understand, these are somewhat artificial problems. Really, if I were to write really realistic problems, each of these functions wouldn't take integers, but they would take like array lists of a certain length that is n, because we're curious about how the runtime grows as input grows. So like if we're running a social network or whatever, and we have 1 million users versus 10 million users, we want to know how much performance degrades. And so in that sense, if we're talking about that example you had with 2-3 trees, there's no reason you would be increasing the size of the B tree nodes over time. Like as you add users to a service, you're not going to increase the size of the B tree or whatever. So yeah, anyway, some philosophy. All right, so I'll kick it over to Aaron.
Hi, sorry, I'm not sure if you mentioned this in lecture, but I guess I was wondering if all objects have hash code representations and hash codes are inherently comparable, then couldn't you write a BST tree that compares based on the hash codes?
That's an awesome question. I like it. Yes. Now, why wouldn't you? Let's see. I've thought about this before, and I remember, okay, yeah, I haven't thought about it in a long time. I mean, yes, you can absolutely do it. There's no reason you can't. There are a few potential concerns. One of them is collisions, because you only have a hash space of 4 billion items in Java. So you'd have collisions, which would mean that if you insert two things, there's just a chance that one overwrites the other if they're in a set. So that's one concern I already see. Does it make sense?
Yeah, okay.
But you could have a tiebreaker, of course, which is just, what would you use though? I guess you could use, let's see. You might be able to make that work. Okay, so that's one reason. what else? I mean, another reason is that often we want our comparables to be somehow semantic. Not necessarily. If you're just doing a set contains, it's no big deal. But if we're trying to do the kind of operations that we had in the KD trees lecture, like nearest or subset or rank or select, they wouldn't really be that meaningful if the hash code was how you decided the ordering. But yes, you could do it. If all you needed to implement was contains and add and delete, then really the main concern is just collisions. And so if you have a perfect hash code, then you would be fine. Yeah. All right, that's a fun question. I won't do it this semester, but some future semester, I'm gonna have to write a midterm problem about this or exam problem. This is really fun.
Okay, thanks.
Cool. All right, Anton?
Hi, as always, I have to pop into existence to
I like
ask my
it.
question.
That's cool. I feel like you've arrived.
Yeah, I need the Star Trek sound for that.
Yeah.
So I want to go back to KD trees. You said something last time that I thought I understood, and then you said, I'm like, oh crap, really? Oh, why is that? So now I feel like I don't. So I don't understand how the ordering works for KD trees. Like, so let's say we have a two-dimensional set, which obviously we wouldn't use a KD tree, but just for the sake of argument. And then we want to group somehow, spatially actually group the points. I just don't quite understand how the fact that we're using one index and then the other not screw up the ordering, and how can we do even a sort of increasing or decreasing order output, say, from that type of an object.
Okay, let me see. Let me pull this up. Okay. So what it boils down to, you can make up an arbitrarily complicated partitioning scheme. Anything works in theory. All you need really is that the subspaces don't overlap. That, for example, that D, it owns this top space and this bottom space. And yes, some of its children may subdivide this space, but as long as it's a hierarchical subdivision of the space, then any point lives like somewhere. Like you've taken the space and broken it into like someone's domain. So I don't know if I quite follow the question. Like, could you repeat just a little bit? Like I feel like I'm almost there, but I just can't quite grok it.
Well, let's say we classify some sort of a point that first, I don't know, we compare it to 5. Like, let's say we compare it to, we compare it to A. So it's has a coordinate smaller than 2, and it ends up on the other side.
Yeah.
I guess what I don't understand is how come we don't end up with a jumbled mess if we take turns in terms of how we arrange them. It seems that at the very least it would be less effective than using the appropriate tree, the appropriate binary, or like a quad tree or octree, tree, whatever, for that type of thing. At least, am I right? At least there, that yes, the KD tree is less.
The tree won't be as good as a quad tree, but it will be a lot more, or potentially. Let's see. So yeah, it'll be potentially less. Of a memory issue. Like, it's actually a good question. Like, KD tree versus quad tree. Where do you? I can say the following without thinking, which is that a quad tree is gonna use more memory because it needs all these links. Like every node has 4 children. Here we have 2 children. So I think we're getting sort of a somewhat crappier partitioning. But what we avoid is that when we go into like octrees or higher, that you can't afford in like a 10-dimensional space to have that many links, because you're gonna have this exponential blow up problem potentially. Well, it's not exponential, but it's exponential in the number of dimensions, right? So if you have 10 dimensions, then you would need 2 to the 10 children. Okay, yeah, so each node ends up being pretty bloated, and most of those links won't get used. So a KD tree, at least the way I conceptualize it, is it's a compromise that you don't have as fine partitioning, but it works pretty well in practice. Now, actually, it's a good question, though. Quad tree performance, is it strictly better than KD trees somehow?
Well, it seems that it will be a lot bushier, or rather, it will be more stout and sort of wide tree than a KD tree, because we're partitioning faster. We're chopping into more. Well, potentially, of course, it depends on the shape of the data.
Yeah, yeah. I mean, there are, of course, balanced variants of quad trees and KD trees. So there's like a KD-B tree, which is a B tree variant of a KD tree that tries to maintain balance. Because the way we describe KD trees and quad trees, they can get arbitrarily spindly. But you're right in the sense that because quad trees have a wider branching factor, they should tend to be more compact. And so my gut feeling is that a quad tree will tend to have better performance than a KD tree. But there may be reasons that I'm not thinking of that I would take some serious thought as to whether a quad tree's performance is expected to be, assuming they're balanced. So if you have a balanced quad tree and a balanced KD tree on a large data set, is a quad tree strictly better? This is an open question for me, though I'm sure the answer is settled. And my guess, but I'm not certain, is that a quad tree is indeed strictly better in terms of performance, but I'm not sure.
Mm-hmm. But my intuition is wrong in the fact that you're going to jumble your categories together. Like this is not something.
Won't jumble. Yeah, and the key is hierarchy. It's understanding that there's no, like, the subrectangles don't overlap in ugly ways. Is the way I would think about it. Like T has these two rectangles, and there's no one else like outside of this part of the hierarchy. Do we have a picture? Let me open up this demo. Yes, good. Okay, it'll be there. So when we go to the end, so D has its two, I'm not showing the rectangles, but like F's rectangles won't overlap D's. Like it owns this. Sorry, I'm gonna draw a rectangle temporarily.
No, just one thing. Would it be fair to say that we're partitioning slower but the same way?
Slower but the same way.
We're putting the lines in the same place, but we're doing this one node offset. So like we're not partitioning into 4, we're partitioning into 2 and then into 2.
Sure. Yes. Yeah, I like that. It's like we're cutting the space less aggressively. We're only doing it in 2 dimensions instead of 4. Yeah. Yeah. I think the key thing I was saying is like D owns this space. None of its siblings or its cousins or whatever will ever overlap this. It's not like F. So the jumble I think you're worried about is like, what if F's rectangles looked like this or something? Like, what if there was some overlap between the F rectangle, which I'll make red, and the blue one? But this can't happen because of the hierarchy. Yeah. Anyway, I think that's what you're getting at, maybe, like the danger you're sensing.
I was confused about, like, let's say if we had like C, the node C, what if it had like a -1? Like, ooh, how did it end up on the right side then? If like C they had -1 as the x coordinate.
Got it. If this had been -1,
then it would end up on the right, on the left side of B.
Like, then it would not have ended up here because it would have been this initial comparison and would have been sent to the left of A.
Yeah.
So it can't happen. This does raise an interesting question: is like if we're using this for planetary simulation, these coordinates can change, right? And so in practice, what you end up having to do is rebuild your KD tree.
Would every step?
Yeah, potentially. There are ways around this, but that's the default way to do things. And that's an okay gamble if for some reason, like if you need to be computing, for example, the gravitational attraction between everything, then it could be a win to spend in time every tick in order to rebuild the KD tree so that all your gravity clusters don't take n squared time. It can work out in your favor, but yeah.
All right, thanks. I really appreciate this.
Yeah, that's a fun question. All right. Okay, Divij.
Yeah, so in the lecture, you mentioned that for negative hash codes, we tend to use math.floormod.
Yes.
I was wondering what exactly that function does, because I didn't understand what math.floormod of -1 and 4, how does it become 3? What mathematical operation exactly that is?
The math operation it's doing is mod as you would think of it in math. That's how I do. So the percent operator is not modulus in math. It's something similar. It's just that it doesn't treat negative numbers appropriately because it can send you outside of the range. So if you do -1 mod or %4 mod 4, it does not keep you in the 0 to 3 domain or range or whatever you want to call it, right? So floor mod does. I mean, floor mod has a more general, let's see, floor mod, let's see. Okay, oops, that's not what I want. Here we go. Okay. Oops. Nope. I want to show floor mod. Okay. Here we go. Okay. Yes. Okay. Oh yeah. So this is literally just this. I was trying to remember. So the signs, the argument's the same. This is the perfect summary, actually. Oops. So they have the same exact behavior if the two arguments are of the same sign. If the two arguments have the opposite sign, then they will behave differently. So specifically, let's see, floor mod. I'm slightly confused. One sec. This is the case I care about. Yeah. So we're using it for this case right here. That floor mod, whenever you're, I think you're modding by, when it's a positive number, you will always get a positive result. That's what I care about. Does it make sense?
Yeah, but what I was wondering is how does it get the numerical value of the result? That's what I want to know.
Oh, like semantically, what's the idea?
Yeah, something like that. I mean, how is it that a floor mod of -1 and 4 is 3? Like, what is the mathematical operation?
Oh, okay, I see. Sorry. I answered too much stuff there. So I'm going to go at this from the strategy of my lecture, which should say 20, and it should say 2020. All right, and so if we go down to floor mod. Okay, sorry, gotta wait for it to load. It's the downside of Google Slides. All right. So the way I introduced it was with this golden apple approach, which is just intuitively, what do you guys think it should be? And there's no right answer to it. And I will show you another picture of it as soon as one day the slides load. Wow, this is very slow for Google Slides. Wow. It's still going. All right. So I guess my question for you is, this question that I asked, what do you think it should be?
I mean, since I watched the lecture, I know it's 3.
Sure. What do you think, though? Where would you put it?
I mean, I would, I guess, as you said in the lecture, I would go through looping and find out that -1 would come in 3. That's how it made sense to me too.
Got it. Okay, and that's the argument basically. So let's say we then did -4. All right, which bucket would you put -4 in?
I guess 0.
0, yeah. So you go back. You'd go -1, -2, -3, -4. If you did -7, you'd go -1, -2, -3, -4, -5, -6, -7, 1. That's the math operation.
I see. Okay, so basically for every negative number, it starts from the bottom of the array and goes up till the amount of the negative number.
Yep.
And that's what your floor div gives you.
Correct. And what's the mathematical function that does that? It is, let's see. They give it somewhere. Floor mod. Oh, they give it in terms of floor div. Anyway, all right. But you can derive a closed form expression for it, but you understand what it's supposed to be conceptually.
And in terms of negative number, the last index has -1 index, right?
The last number has index -1?
No, sorry, the last index has index -1.
What's the last index? Oh, -2 billion, whatever.
No, for example, in this array of length 4,
yeah,
the last.
Yeah. -1 is always the last entry. Correct.
Yeah. Okay, thank you.
Cool. All right, Anton, go ahead. You got the last word, and then we're going to bail.
Sorry, I just forgot to lower my hand.
Oh, okay, cool. Sounds good.
About that. I thought I did. I clicked on it, but I didn't.
No problem.
Sorry.
Right.
Thank you.
Anything else anybody's got?
Yeah, Josh.
Yeah.
Yeah, I have a question for you, like a private question after.
Okay, cool. I'll kick everybody else out and we can just chat. Actually, you know what I'm gonna do? I'm gonna send you a link to, oh, wait, Sufi, you can't raise your hand. All right, I'll get to you in a sec. So Sufi, let me take your question. Go ahead.
Okay, sorry, I should have said something, but so I had a question on like it's an exam prep 6 problem. It's the one. Well, actually, I have a question for both F4 and F5, but I know that we're out of time, so I'll just ask it for F5.
Yeah.
So let's see if
this
like
is exam prep. Which one?
6.
Okay, let me share my screen real quick just so I can make sure I got the right thing. So we got 6 exam prep. This one?
Yeah.
Okay.
So looking at F5, which is the second one. So okay, so the fact that we're doing n mod 10 means that at most it's going to run 9 times, so it's constant, right? And then
yeah, I guess so, technically. Though I'm going to stop you there because in general, there's always a max integer. And so you could argue, well, if we're doing I equals 0 to n, it can never be more than 4 billion. So really it's a constant. So like these problems are, you've identified a little tricky thing about these problems, which is that in Java, integers can only be so big. And so one sort of like underlying assumption we're making is that in fact, the integers can be arbitrarily large, because otherwise you could trivially say the runtime of every function is constant because the integers can only get so big. Does it make sense?
Yeah.
So I love that argument that yes, it could only be up to 9 times, but what's more fundamental there? Like, let's imagine the n can get arbitrarily big. How many times could this run? Oh wait, never mind. I'm so dumb. I thought this was
isn't n mod 10 always just the last?
Yes, sorry. I thought that the problem was n was dividing by 10 every time. Okay.
No, so it's dividing by 10 in the.
All right. Yes, you're right. It can only run a constant number of times. Yes. Okay.
Okay, got it. So then when we call f of 5 on n divided by 10 and then m divided by 10, so each time we're dividing n by 10, and in our like base case we return if it's n less than 10, and so the like runtime should be theta n because we don't really care that it's getting divided by 10 each time. Is that like the right way?
Well, we do care that it's getting divided by 10 each time though, because if it starts as, you know, 1,000,000 and then it's 100,000 and then then increasing n by 1, or like, let's say, okay, sorry. The fact that we're divided by 10 is pertinent. If it had been n minus 1 here instead of n divided by 10, you would get a different runtime.
Okay. And that's because of the base case that we have, which is not the, our...
Yeah, I mean, it is because of the base case, but I'd say there's something a little more fundamental. Like if this said if n equals 1 or something, it would still be the same thing.
Okay.
Yeah.
Then if we had m in the base case,
yeah,
would we consider m in our runtime?
No. Well, maybe we would. Good question. How about Wednesday? Let's table this question till Wednesday, and then we can give it a closer look.
Okay, sounds good. Thank
cool.
you.
All right, and then by the way, what I'm gonna do is, can you send me a quick email, Vivek, and then I'll send you a link to another Zoom, because this one's being recorded, so that way you don't have to.
What do you mean send you an email?
Just send me an email to hug@cs, and then I will immediately reply with a Zoom link.
Oh wait, what's your exact email? Because I found 2 when I was in the directory.
So there's another guy. There's a grad student named Josh Hug. Don't email him. I'm hug@cs.berkeley.edu.
Hug@cs. Okay, got it.
Yeah. All right. I'll talk to you in a second.
Cool.
Okay. Talk to you then. Thanks, everybody.